Okay, I am going to do proof 22.3, which is essentially saying that if we have some convex domain U and some phi defined on it, that phi is the exterior derivative of some function if and only if d phi equals 0. So the first way and the easiest way is to assume the phi equals df. So we know if phi equals df, and d phi is equal to the exterior derivative of the exterior derivative of f, but as we've shown in another proof, that is equal to 0 always. So this shows the first way that phi, if phi equals df, then d phi does equal 0. So I will erase this. And now we're going to assume that d phi equals 0. This is the second and slightly more challenging way to prove it. So first let's take a function f and define it to be the integral on a path from x naught to some x function value of phi over that path. And we'll use this later in our proof, and I'll come back to that. So a good proof always includes a picture. So say this is our convex domain U. Then we're going to have some point x naught in it, some point x in it, and some point x plus hv. And so we're going to have paths running from x naught to x to x plus hv, and x plus hv to x naught. And these, though they might not look like it, are going to be straight line paths. Because we know that if U is a convex domain, then every point between the 2 points in the convex domain is also in the convex domain. So we know that each of these 3 straight lines is in U as well. But we can draw a line between any 2 of the 3 boundaries and hit any point within this triangle. So we know that the entire triangle, which I'm going to call T, lies within the convex domain U. So we know that phi is applicable over all points in and on the boundary of this triangle. So now, if we employ the use of Stokes' theorem, then we see that the integral of d phi over the triangle is equal to 0, since d phi is constantly equal to 0. But we see that this is also equal to, by Stokes' theorem, the integral of phi over the boundary of the triangle, which is equal to the integral over all 3 of these edges. So the integral of phi from x naught to x, plus the integral of phi from x to x plus hv. And for sake of having 2 integrals that start at x naught and at something else, we're going to instead take minus the integral of phi from x naught to x plus hv, whereas we could have added the integral from x plus hv to x naught since we're reversing the path length. But this is going to be more useful. So we see that 0 is equal to these 3 integrals. But we've defined f to be equal to the integral of phi from x naught to x, and that is what that is. So we have f of x here, plus this integral that we don't know much about, so we're going to leave it as is for now, minus f of x plus hv, since this is the form of our definition for f as well. So this is the integral we have, and we can rearrange it to say that f of x plus hv minus f of x is equal to the integral from x to x plus hv of phi. Now, if we divide by h and then take the limit as h approaches 0, we're going to get on the left the limit as h approaches 0 of f of x plus hv minus f of x divided by h. But we know this to be equal to the derivative of f of p anchored at x and spanned by v. So if we do the same thing on the right now, then we can get the limit as h approaches 0 of 1 over h times the integral of phi from x to x plus hv. So in order to solve this, we can take gamma and parameterize the curve on which we have it defined. So gamma of t is equal to x plus hv t, where t is greater than 0 and less than 1, so that we run out the entire length of that line. So that makes gamma prime of t equal to h v. So this integral becomes the limit as h approaches 0 of 1 over h times the integral from 0 to 1 of phi acting on the parallelogram anchored at x plus hv t hv dt. So what happens here is that this h and this h cancel, and then if we take the limit as h approaches 0, so does this term. So we're left with the integral from 0 to 1 of phi p anchored at x ran by v t. And the integral now, since no t's are in the equation, just is equal to 1 times phi px anchored at v. And we see that phi of px anchored at v is equal to df pxv, and to say it more succinctly, phi equals df. And we have proved that if d phi equals 0, then phi is equal to the exterior derivative of some function, completing our if and only if proof.